Okay, let's get started. So we're going to look today at statistics. And because I've got limited time, I've chosen these topics, 3 topics: the chi-squared distribution, continuous probability distributions, and independent random variables. Now, the statistics module is Unit 2, so Friday the 19th of May. Moving on to the specification. So the exam board's advanced information for 2023. The stuff in yellow highlighted, that's what they're suggesting is going to be in the exam. One of the things that I noticed is probably going to be omitted this year was this thing in the red box, using the chi-squared test to test for association in a contingency table. So contingency table is what you might call a two-way table. I put an example just below down here. They are suggesting that that is not going to be examined this year. However, I would definitely cover it. If you're doing past papers, it's still worth doing just in case there's some kind of error. They also highlighted that you need to understand pooling, and that's where we group the expected frequencies together if they come to a value less than 5. Let's have a look at an example question. So I've taken this from a different exam board, but it's quite similar to the ones that you'd be presented with. We've got a table at the top and it shows the number of hurricanes per year in a certain region. So this is recorded over 80 years. So I'm guessing this number here, for instance, that represents 12 years where we had 7 hurricanes during the year. If I look down here, there were 0 years with 0 hurricanes, so it must be an area where hurricanes do happen. Write down 2 assumptions that will support modelling the number of hurricanes per year by a Poisson distribution. So for a Poisson distribution, we want various things. So for this one, we want the hurricanes to occur at a constant average rate. Now, usually you have to refer to the actual thing that is in the data set. So hurricanes, you actually need to mention hurricanes. They occur at a constant average rate. Probably need a little bit more because I'm just looking at how many marks this question is worth. It's worth 2 marks. So I probably need a second piece of information there, and the other thing I might put is they are independent, or you could say they occur singly, so you can't get more than 1 hurricane happening at a time, although I'm not a weather expert, so I don't know, maybe you could. Show that the mean number of hurricanes per year from table 1 is 4.4875. So our mean number of hurricanes, and this is kind of going back to maths that you might have done in year 7, the mean from a frequency table, you're doing the number of hurricanes times the frequency, add the number of hurricanes times the frequency, and you're just doing that for each of the parts of the table. And then you keep going all the way to the end, 7 times 12 divided by the total number of hurricanes. I think it says here we're looking at 80 years, so we're dividing it by 80 years. That gives us 4.4875. So far, we haven't done any of the chi-square testing. Now, part C, use your answer to calculate the expected frequencies given in the table. So often they will give you a table and there's only 1 or 2 values that you might need to fill in because it's quite a repetitive process. Once you've found one, it's quite easy to find another. So because we're saying it's a Poisson distribution, we might say that our hurricanes are distributed with a Poisson distribution. Our lambda value, that is the mean, so 4.4875. Because our mean is lambda. Then if we look in our formula book, here's the equation that helps us work out the probability. So the probability that the number of hurricanes in a given year is 2. So we're just going to work out this one. Equals, and then we put the numbers into the formula, e to the minus lambda, so minus 4.4875 times lambda 4.4875 to the power of x is 2, divided by x factorial, so 2 factorial. That equals 0.1132. That's a probability. That's not the actual expected number of outcomes. So the expected number is 0.1132 times the number of years, 80 years. That gives us 9.06. So here, that's 9.06. If you do the calculation for S, we get 15.205. Now I've used the formula here, but for this bit here, you could just use your calculator. So use calculator as an alternative. So on your calculator, you're looking for the Poisson probability distribution function. That's the mode that you're going to use, and you should have been shown that in your lessons. Now, we haven't actually done the chi-squared test, so we're going to move on. That would be a nice starter for a question. Part D, so this is still the same question. For part D, test at the 5% level of significance whether or not the data can be modelled by a Poisson distribution. So I still got my same table at the very top. I filled in red here R and S. These are the expected frequencies. I've noticed that these guys here, well, the first two columns, when I add them together, that gives me 4.94, and you want your expected frequencies to be 5 or greater. So you need to pool these together. And when we've pulled them together, that's how we've got the 14 here. If you add them together, that's what you're getting. So you need to remember to pool them. Very often when you're doing practice questions, you might just be looking at the last few columns and adding those together, but do remember to look on the left-hand side and pull together anything there. So for a hypothesis test, it does say state your hypothesis clearly. So our null hypothesis, the hurricanes can be modelled with a Poisson distribution at an average rate of 4.4875 is a good fit. And then the alternate hypothesis is that the Poisson distribution with an average rate of 4.4875 is not a good fit. So we probably should be explicit about which about our lambda value, because it could be that it is a Poisson distribution just with a different lambda value. Now, to work out your chi-squared contributions, you're doing the observed, take away the expected, you square that, and then you divide it by the expected value. So we'll just do one of them, and then I'll show you what the sum is. So I'm taking kind of these bits of data here, and that's what I'm going to use. So observed is 7 minus 14 all squared divided by the expected, so 14, and that gives us 3.5. Now we're kind of saying, look at the difference between these two numbers. So look at the difference between 14 and 7. If there is a big difference, that's bad. That probably means that this isn't a Poisson distribution. If there is a small difference between 14 and 7, that's good. That means that we, maybe we are looking at a Poisson distribution. So if I look at some of these other numbers, like look at the difference between these two numbers here, they're very close together. The same here. These two are very close together. So the closer they are, the better. The further away they are, the worse. It just so happens, I think, that these two here are some of the furthest away from each other. So these two actually give a very good big contribution, and a bigger contribution is worse. In our formula, the reason why we do the observed minus expected and we square is for two reasons. So the squaring, that's going to basically turn any negatives into a positive, because we would have got a negative coming out here. It's also going to magnify any large differences. So this is a large difference, and it magnifies that. It makes that, gives that a greater weighting. Now, if I were to do this process for all of them, you get your test statistic, which is the sum of all of what we've just done. And if you add them together, you're getting 6.55. So that 3.5, that actually contributes a lot to that 6.55. So those are the chi-squared contributions, and a bigger number there is worse. Now, we're going to do our test. We want to think about the degrees of freedom. So the degrees of freedom and that's represented by this Greek letter nu. Looks like a V, but it's this symbol here. So we've got, well, 1, 2, 3, 4, 5, 6 columns in our table. We take away 1 degree of freedom because our expected sum had to, we had to get it to sum to 80. So expected summed to 80. So this value here, you could say that is predefined. We have no choice but to put 13.39 in there, because if we didn't put that in there, they wouldn't sum to 80. We also, in this example, lose another degree of freedom, and I don't think I've actually seen this come up in our exam board, but the degree of freedom we've lost is because we have estimated our lambda value, and that happened in part B. We estimated lambda. If you are given lambda, so if you're told what the Poisson distribution is, then you wouldn't take away this this extra degree of freedom, but because we've estimated it, we're going to take that away. So our degrees of freedom is 4. So what we're looking for is we want to find our chi-squared value, and we're looking for the 0.95 value. Our degrees of freedom is 4. So on here, let's think on the graph what we do want and what we don't want. So up here, this is the formula book. That's why it's in green here. This here, that's the region that we do not want. That's 5%. We would like our value to be kind of down here. This is like the safe region, and that's 95%. Now on my table here, I'm looking at the degrees of freedom being 4, so it's this one here, and I'm sort of going to pull my eyes along until I get to here, because I need it to be the 95th percentile. So that value is 9.488. On this graph here then, this is telling me that that here is 9.488. The contributions that we've summed together are, I don't know, 6.55. They're about here somewhere. So anything down here is safe. That is saying that we could use the Poisson distribution to model this. Anything greater, anything up here, means that we must have lots of differences between these numbers here, and the differences must be so big that it's giving us a dangerous value, which would be up here in this sort of bad 5% section. So as a closing statement, we would say that 6.55 is less than 9.488. Therefore, we have insufficient evidence to reject the null hypothesis. So insufficient evidence to reject H0. You should then relate back to the original problem. So we could, as a closing statement, you'd say something along the lines of hurricane frequency can be modelled with a Poisson distribution. So hurricane frequency modelled as Poisson distribution with 4.4875 as the lambda value. Now, if we just take a look at the chi-squared distribution, I'll keep these. Yeah. So the chi-squared distribution, it changes shape according to the degrees of freedom. So as we increase the degrees of freedom, it kind of pushes the curve further up. That kind of makes sense, because the more degrees of freedom that you have, the more likely you are to have a discrepancy between the observed and the expected. So the this up here means that our values could be a lot higher up. Our degrees of freedom was 4, so I'm just going to change this to 4. And then if you look down here where my mouse is hovering, that's giving us a probability of 0.08. So this red area is 0.08. If I increase this, we were getting a value of 9.488. So I think I can only get it to like 9.5. There you go. Can you see the area here is 5%? The test statistic, which is this line here that I'm pulling in, our test statistic was 6.55. So if I put 6.55 on here, well, 6.6, that's pretty good. You can see that that is well within the safe area. Anything in here means that our contributions are not big enough to cause us a concern. So that's kind of a graphical representation of what's happening. Let's come back to the PowerPoint. And on this page is a question that you could try. And I'll just pause there. This one isn't a Poisson distribution. I think this is a binomial one, which is the other type of distribution they might want you to compare. They also might want you to compare a uniform distribution. And then on this next slide is the mark scheme for it. Now, I'm just going to come out of the PowerPoint because it seems to have this annoying menu bar at the bottom. I'm just going to see if I can get rid of that. I might not be able to. See? Oh, it's still there. Oh, we'll just keep going. Continuous probability distribution. So in yellow, I've highlighted what they are suggesting we might need to know for this year's exam. It looks like they want us to be able to find the median and the quartiles and percentiles, not the mean, the variance, and the standard deviation, which I don't know, I find that that could be more tricky actually. Let's just come out of this and see if this will, there we go, that's better. So here's a question on a continuous probability distribution. Again, this is not taken from our exam board, but it's very similar. The lifetime in tens of hours of a battery has a cumulative distribution function given by this. So cumulative, they are going to use a capital F here. That means they have already done the integration. So they've already integrated f of x. The function here then is defined for values between 1 and 1.5. When I'm looking at this, if I think tens of hours, that means that we're saying we're between 10 hours and 15 hours. That's how long these batteries are lasting for. And anything under 1 or 10 hours, there's no batteries. And then anything over 1.5, which is 15 hours, well, there isn't anything there. So none of them are lasting more than 15 hours. Now, if you put a what's this value? If you put a 1 into this function, that's telling me that the area up to this point should equal 0. If you put 1.5 into this function, that is telling you the area up to that point is 1, which is that number there. So for part A, let's have a look at this. Find the median of x, giving your answer to 3 significant figures. So the median, f of m, that's where our area is kind of halfway between these two. So our area must be 0.5. That's what we want. So let's write this out. 4/9 times m squared plus 2 times m minus 3 equals 0.5. And then we're just going to go ahead and solve this to find some different values of m. If I kind of multiply through here, I'm getting m squared plus 2m minus 3 equals 9/8. And then if I pull the 9/8 to the right-hand side, I get m squared plus 2m minus 33/8 equals 0. Solving, you get m as 1.2638 or negative 3.268. So you've got 2 answers, which you'd expect from a quadratic, but only one of them is valid. Because our batteries range from 1 to 1.5, the median must be between 1 and 1.5. So we're going to reject the negative one because it's not in our range. If I got a positive one, let's say I got a positive, I don't know, 1.7, well, that's still outside the range 1 to 1.5. So it needs to be in that range. So our median is 1.26, and I think it says in the question, give your answer to 3 significant figures. That makes sense as well. It's roughly between 1 and 1.5. It's nearly exactly between them. Part B, find in full the probability density function of this random variable. So this function that we've been given is kind of the integrated function. So what we need to do is we need to differentiate this. So for part B, that's what we want to find. We want to find the derivative of that. If you differentiate it, then we get 8/9 x plus 8/9. Okay, I multiplied out the brackets and then I've differentiated it. However, I'm looking at this, I'm thinking 3 marks. That seems very easy for 3 marks. There must be something more to it. And then you look at the original question and you realise I do need to be more specific with this. So because this is what we call a piecewise defined function, we need to define it for all the values. So here, f of x equals, and this is only valid 8/9 x plus 8/9. That's for all the values between 1 and 1.5. and then the probability density function will drop to 0 for everything else. So 0 otherwise. And we'll have a look at this on a graph in a minute. So you do need to say what's happened. So you need to say that's the probability density function for the region that we're interested in. Otherwise, we have a probability of 0. And it's kind of going back to what I was saying. Our batteries either only last between 10 and 15 hours. There are no other batteries outside of that are lasting any other time. For part C, find the probability that X is greater than 1.2. Remember, that is 12 hours. And that's going to be important because when I look at part D here, it's talking about 12 hours, so I'll probably use that answer in part D. So the probability that X is greater than or equal to 1.2 is equal to, now there are various ways of doing this, but sort of an easy way of doing it would be to do 1, take away the probability that X is less than 1.2, because what this function does is it works this bit out for you. So here we're doing 1 minus f of 1.2. This is the cumulative distribution function. So it is a function that allows you to work out the probability up to a certain point, not above a certain point. If you do this, you get 0.6267. So I put the number 1.2 into my function here, and this is what I've got coming out. Let's have a look at this on a graph. In fact, I will just do the last part as well before I move to the graph. So part D, find the probability that a lantern will still be working after 12 hours, but let's read the first bit. A camping lantern runs on 4 batteries. All of them must be working. So I need all 4 of them working, 0.6267. The probability that they're all working is 0.6267 to the power of 4. You're timesing it by itself 4 times. You can imagine a tree diagram with working, not working, and then just going through 4 sets of working. You're going to multiply them together and you get 0.154. That's the probability. Now let's look at this function in Desmos and just have a play around with it. So this is what the function looks like. This is because I haven't actually put the full function in. The purple line is giving us values outside of our region. Our region is obviously the red bit between 1 and 1.5. Really, if I'd drawn this correctly, I should have drawn the purple line so it dropped to 0 when it got to 1, and also so it dropped to 0 when it got to 1.5, but I was a little bit lazy. I should have put some limits on here. However, the red bit, that's the bit that we're interested in. You can see, because this is finding the area as we go, you can see the area here is 1, is where my mouse is hovering. If I pull this bit down here, it's obviously reducing the area. So if we go, let's change this, actually, let's change the top one. I think they were talking about 1.2, greater than 1.2. So if I put this to 1.2 here, there we go. This was the probability that we just worked out, 0.626666 recurring, I guess it is. If I don't know if they'd asked this, but if they said, what's the probability of a battery lasting exactly 12 hours? So that means I'd be interested in the probability that X is equal to 1.2. And if I did that, I'm sort of showing you what that would look like on a graph. Can you see that it's basically a line connecting that dot there and a dot there, which we can't graphically show here, but the probability there is 0. So when we are using the a continuous probability distribution, we won't be finding the probability that something equals exactly a certain amount. We either find something being less than or greater than a certain amount. Let's go back to the slides. Oh, hang on. Now, on the next slide is a question that you could try yourself. I'll just pause there. And then the mark scheme is here. And then we'll move on to our last topic. So we're looking at independent random variables. And there's a lot of stuff that they could ask you here, so I'm just concentrating on one bit. There's quite a lot of stuff that they give you in the formula book as well. So if I jump forward to the question, what we've got in green, these are the things that are in the formula book. So at the top, it tells us what happens if we combine random variables up here. Down here on the next box, it tells us how to find the mean for a binomial, the variance for a binomial distribution, which we could definitely be asked. Then this green box here, you may have not, well, you should have investigated this, but the variance, I prefer to see this in a more user-friendly way, that here we've got e of x squared minus e of x all squared. So this formula at the bottom here, that's how I usually prefer to see it. Just to remind you what the e of x is, it's like the expected value. So I've got a sort of a simple distribution at the bottom. This could be the outcomes when you roll a dice, and you do the number on your dice, so 1 times the probability of it happening, and the number on a dice times the probability of it happening, and you just do that and you repeat the process. For this one we get 3.5. For the e of x squared value, you do the number on the dice squared times the probability, add the number on the dice squared times the probability, and you just repeat that. This one is giving me 15 and 1/6. And then you could use these values to then go and find the variance. Let's do the question, otherwise we might run out of time. So part A, part 1, I think I can fit it in here actually. We've got a binomial distribution and it tells us the parameters. The number of trials is 20, the probability is 0.4. So your expected outcomes equals, and they kind of give you a clue here, the expectation is the mean. So if you look here, it tells you what the mean is, and that's all you do. 20 times 0.4. That's 8. So I did n times p. E of x squared, now I'm going to need a little bit more space down here, so I'm going to go down here. Because you sort of look at e of x squared and you might think to yourself, well, hang on, how am I going to find that? Because there isn't a formula that lets me do that. We can find the variance, so that's what we're going to do. The variance of x, and we've got a formula over here for the variance of the binomial distribution. NP, so 20 times 0.4 times the probability of the thing not happening, so times 0.6, that equals 4.8. And I'll just write what I've done there, 20 times the probability times 1 minus the probability. Then if we look at the formula, the variance of x equals e of x squared minus e of x all squared. And if I put the things that I've got into this formula and rearrange it, I'll be able to find e of x squared. So the variance is 4.8. E of x squared, that's the thing that I want to find. Take away, and then 8 is the expectation. 8 squared. This gives us e of x squared equals 68.8. So that's sort of A. Now, I chose this question because it combines a binomial and a Poisson distribution together. So for part B, we're now talking about a Poisson distribution with a mean of mu. So if we just check, when we look at our Poisson distribution, the parameter in here, that is both our mean and our variance, and that's going to be useful in this question. So the mean is equal to E of y, and I'm using y because it told me it's a different letter here, and that equals lambda, and that also equals the variance. So all of that's quite useful. So my variance of y equals E of y squared minus E of y all squared. And I'm just using the formula down here. Let's put the numbers in that I've got. So I've got the variance. Oh, hang on, I haven't got the variance, but I do know that the variance is lambda. And that equals E of y squared, which they give me in the question, 9.36, minus E of y squared. And I know that E of y is lambda, so we get minus lambda squared. And so we've ended up with a quadratic. Lambda squared plus lambda minus 9.36 equals 0. If you solve this, you get lambda is 2.6 or negative 3.6. We will reject our negative. And so lambda is 2.6. Is that what it's asking for? Well, it's asking for the mean. So lambda equals mu, which equals 2.6. Now, part C, the random variables x and y are independent and u equals x times y. Determine the variance of u. So for this one, we're combining the two random variables above, which that's quite common for our exam board. So the variance of x, y equals, and you take the individual e of x squared values, so e of x squared times e of y squared, and you take away the expected values multiplied together, e of x times e of y, all squared. Run out of room a little bit there. They kind of give you this bit here in the formula book. Let's continue. So what are we finding? Oh, the variance of u. So the variance of, well, because x, y is u, that is 68.8 times e of y squared. Now I need to just look back through my working and see if I've been given e of y squared. Oh, they gave it to us up here, 9.36. Take away, and then we've got 8, which is e of x times e of y, which I've just worked out as 2.6 all squared. So if you put this into a calculator, you get 643.968. Take away 20.8 squared. And that equals 211.328. So that's a question where you, well, definitely need to get your formula book open and have a look through it, but you should know the mean and the variance of the binomial and the Poisson distribution, or at least know that it's in the formula book, and you've had to use both in the question to answer the entire question. Now on the next slide, this one is just a binomial one. And I'll just pause there so you can try that one. And then if I move on to the next slide, it's got the mark scheme. And then the next slide is just another question that you could practice. I'll just let you try that. And then the final slide is the mark scheme for that.